Okay, welcome back, and today we're going to continue on with confidence intervals, and we're going to talk now about a new parameter which is going to be the population proportion. And so how do we calculate or construct a confidence interval for the population parameter, the proportion? Okay, so now we're going to talk about P. So this is going to harken back to chapter 6 when we talked about the normal approximation for the binomial random variable. So we're going to look at the same thing. Okay, so remember, from chapter 6 we said, okay, if we look at x as a binomial variable with n and p, right, then we could use a normal approximation by using the normal approximation to this would be x is approximately normal. Now what would be the mean and the standard deviation? Well, based on a binomial variable, well, we know that the mean, right? So the mean is equal to n times p, and sigma is equal to the square root of, we'll write it this way, the square root of n p q. Okay, and so we found in chapter 6 that this x can be approximately normal as long as we have a large enough sample size, and we could use for the mean np and for the standard deviation the square root of npq. And then we also talked about, well, if we look at the proportion, well, we know that p hat, right, is just equal to x times n. And so based on this, it makes sense that this would, x divided by n would also have approximately normal distribution, and then we just divide everything by n and we get p and the square root of pq divided by n. So we saw that in chapter 6, and I showed how to derive that. Okay, so what we're going to do is we're going to use this distribution for constructing a confidence interval. So we need to know the distribution of p hat, the sampling distribution, right? So again, this is chapter 7, okay? So if we know that the sampling distribution is this, then we could calculate the confidence interval based on this normal distribution, as long as we use this as the standard deviation, okay? So let's use that. So okay, so now p hat is going to be approximately normal with the mean of p and this standard deviation of pq divided by n. And that, of course, is going to be if 3 conditions are met. One is that n is greater than or equal to 30, right? So that goes without saying. That's what we used for sample size, right? But in addition to that, we also need to know that n times p is greater than or equal to 15, and n times q, which is greater than or equal to 15. And remember, q is equal to 1 minus p, okay? So basically, the expected number of successes and the expected number of failures both have to be at least 15. Now, the reason why that is because if you remember, for a binomial random variable, if p is equal to 0.5, you get a nice symmetric distribution. And basically, you'll always get, so if you have the minimum sample size of 30, right, and you take half of that, you're going to get 15 successes and 15 failures, right? So if p is 0.5, then you automatically get all 3 requirements as long as n is greater than or equal to 30. So if p is equal to 0.5, really all you need is the minimum sample size to be at least 30, and the other two conditions will be automatically met. But what if P is not 0.5? What if it's significantly bigger or smaller than 0.5? Okay, in other words, what if P is close to 1 or really close to 0? Well, then you need a bigger sample size in order to make sure that the distribution of P hat is going to be bell-shaped and symmetric. Okay, so if you have a small P value, a small value for P or a large value for P, then the distribution for the binomial variable tends to be more skewed, and therefore you need a bigger sample size to make sure it's bell-shaped and symmetric. So that's why these other two conditions are added. These make, as long as all three, that makes sure that regardless of what P is, we'll have a approximately normal distribution. Okay, so just keep that in mind. Now, if we do have these conditions met, then we can assume that P is approximately normal using the central limit theorem. And now, what we also have is we can use this formula, or this formula for the confidence interval. So confidence interval for P now. Now remember the two pieces, the anatomy of a confidence interval. You've got the point estimate, and the point estimate in this case is going to be the sample proportion, which we denote P hat, right? So P hat, so remember P hat is equal to X over N. Plus or minus, since we're dealing with a normal distribution, it's bell-shaped and symmetric, so we can add and subtract the margin of error. So it's going to be our margin of error, which is going to be, again, with the Z alpha divided by 2, because we're dealing with normal, so we're going to have our same Z score that we had before, or critical value, I should say. So Z alpha divided by 2 times the standard deviation of what? Of P. The standard deviation of P is this, but we can't use this. Why? We don't know what P is, so we don't know what Q is, right? So in other words, what we're going to do is we're going to use the standard error, what we call the standard error. And the standard error is just we're going to replace P and Q with the sample statistic. So it's going to be P hat times Q hat over N. And we take the square root of that. Okay? And so this is the formula for constructing a confidence interval. So just like before, we can either use the table, right, the Z table, or we can use inverse norm to get our critical value. Once we have our critical value, we'll be able to have P hat from the problem. We'll be able to construct this, and we'll also have N from the problem, so we'll be able to figure out everything in plug and chug. The only thing we're going to need to know is what Z alpha divided by 2 is. So again, the standard normal table will give it to us, and inverse norm will also give it to us. But there's also a function on your calculator that will give you this interval without having to figure out what the critical value is, and that is going to be 1 prop Z int. Okay, so that's going to be under the tests menu. Okay, so go to stat tests, scroll down until you find this. This is the function that will give you the confidence interval for the population parameter P, the population proportion. Okay, so we'll do an example. We'll do actually a few examples of this and to show you how this works, and really just practice using this. Practice using the formula, practice using the function calculator. Obviously, I'm going to prefer using the calculator and using the 1 prop Z int function to give you the interval, and then all you have to do is interpret it, right? Okay, so let's do some examples now. Okay, let's see here. Okay, so the first example we're going to do is this. So we have, suppose that a marketing research firm is hired to estimate the percent of adults living in a large city who have cell phones. "500 randomly selected adult residents in the city are surveyed to determine whether they have cell phones. Of the 500 people surveyed, 421 responded yes, they own a cell phone. That they own cell phone. Using a 95% confidence level, compute the confidence interval, compute the confidence interval estimate, or confidence interval for short, for the true proportion of adult residents in this city who have cell phones." Okay, so that's the problem, right? So the first thing I would do is pause this, write down all the information, see if you can solve this without looking at the solutions. Okay, so do that now, and then see if you get the correct answer on your own, and then come back and see if you did it right. Okay, so the first thing I'm going to do is writing down the information. Okay, so it says 500 randomly selected adult residents in the city were surveyed. So what is that? That's going to be our N. Okay, so N is 500. And then of those 500, 421 said yes. Well, what's that? That is going to be our X value, right? So X is 421. Well, if that's our X value, then what's our number of failures? Well, it's going to be N minus X, right? So N minus X is equal to what? Well, it's going to be 79, right? Okay? And both of these add up to 500. So now, this, if you haven't figured it out, this is what is going to be our N times P hat, right? And this is the same as N times Q hat. Well, remember our three conditions, right? Our three conditions need to be met. So this has to be bigger than or equal to 30. Check. This has to be bigger than or equal to 15. Check. And this has to be bigger than or equal to 15. Check. So what do we know? Well, we know that the distribution then for P hat is going to be approximately normal with a mean of P and a standard deviation of PQ divided by N. Okay? So that means we can use our formula for the confidence interval. So our formula, again, and this is going to be a 95% confidence interval, right? So our confidence level is 0.95. And that's all we need. Now, let's write down the formula first. So our formula for the 95% confidence interval for P. And that's going to be P hat plus or minus our margin of error, which is Z alpha divided by 2 times the square root of P hat times Q hat over N. And so now, I'm going to do it all three ways. I'm going to use the table, I'm going to use the calculator to use the formula, and then I'm going to use the calculator to get the interval directly. Okay? So now, do we know P hat? Yes. P hat, or no, we don't know P hat. They give us X and they give us N minus X. So we can figure out P hat by using our formula. So P hat equals X divided by N, which is 421 divided by 500. Okay, which is going to be 0.842. Okay, so that's going to be P hat. So now we've got this piece. Now we've got N, we've got P hat, so that means Q hat we have. So Q hat, remember, is just 1 minus P hat. So that's just going to be 0.158. And so now we've got everything to plug and chug except for our z-score. Now, again, if you use the table, right? So use the z-table, or if you use inverse norm, you should get the same answer, which is going to be 1.96. Okay? So now, make sure you know how to use the table and inverse norm. Remember, for inverse norm or the z-table, you have to make sure you use the correct area to the left, right? So in this case, I always show the area to the left of the positive one, okay? So z alpha divided by 2. And so here's the critical value. And the area to the left is going to be the middle area, right? What's the middle area? That's our confidence level. Remember, the confidence level tells us the middle area between our two critical values, right? So we get the negative z alpha divided by 2 and positive z alpha divided by 2. We know that the area between these has to be 0.95. That's what we know about the confidence level, okay? And then what happens? Alpha. Well, what's alpha? Alpha is the area in the tails. Don't forget that. Alpha is always the area in the tails, which is just 1 minus the confidence level. So alpha equals 1 minus the confidence level, which is 1 minus 0.95, which equals 0.05. And then half goes in each tail. So that's 0.025 here, 0.025 here. And so what's the area to the left? Well, it's going to be 0.95 plus 0.025, right, for this tail. And so the total is going to be 0.9750. Okay? And so if you look for this area on the table, you're going to get the z-score of 1.96 that corresponds to this. Okay? Also, if you use inverse norm, remember you can use inverse norm by plugging in the right ones, the right numbers. So inverse norm, the first argument, remember, is area to the left. So if you put in area to the left, you're going to put in the 0.975 and then followed by the mean and the standard deviation. Well, what's the mean and standard deviation for this z-score? Remember, it's a standard normal distribution. The fact that it's a z-score tells you that we have to use the standard normal distribution, so the mean is always 0 and the standard deviation is 1. So that's what we put in. And then this is going to also give you the 1.96. Okay? So once you have the 1.96, then it's just plug and chug, right? So what are we going to do? We're going to plug in our 0.842, so 0.842, that's our point estimate, p hat, plus or minus 1.96 times the square root of what? 0.842 times 0.158 divided by 500. Okay, and we take the square root of that. Okay, and if we do that, what do we get for our margin of error? I don't have my calculator with me, so my margin of error turns out to be 0.032. So if you calculate this out, you get 0.032. And so now if we add and subtract our 0.03 or 0.032 from this 8.42, our critical value we get is going to be 0.81, comma, 0.874. Okay. Now, when it comes to proportions, we always go at the 3 decimal places, and we always want to change it to a percentage. Much easier to deal with a percentage than to work with decimals when it comes to proportions. So we can also write this as 81.0% to 87.4%. So now we can interpret this much easier. Okay? So the interpretation, again, remember, is going to be at a 95% confidence interval. So we're going to say we can be 95% confident that the true proportion of what? The true proportion of people living in this city who, what does it say, yes? that they own cell phones, right? So we're saying that the true proportion, we are 95% confident that the true proportion of people living in the city who do own a cell phone is going to be somewhere between 81.0% and 87.4% of the population. That's it. Okay? So I hope that makes sense. So I showed you using the function or using the formula, using either the calculator to get your z-score or using the table to get your z-score. You then just plug and chug into the formula and you'll get the answer correct every time. Okay? Now, let's use the other function. Now, the cool thing about using the calculator is that you don't have to worry about any of this, but don't forget this, okay? Because you'll still need to know how to get the z-score from time to time, okay? Even on an exam situation, if I ask or your teacher asks, hey, what's the critical value for this situation? You might have to use inverse norm or the table, okay? So, let's go on. So now, let's use 1 prop z int. So now, the things that you need to put into the calculator are 3 things. You're going to need to put in the sample size, you're going to need to put in x, and you're going to need to put in the confidence level. That's it. Frequency, remember, you leave alone. You're not touching that. These are the only 3 things you're going to change. You have to put in the sample size, n, x, and confidence level. Okay? That's all you have to do. So in this case here, all you would put in is n is equal to 500, x is equal to 421, and the confidence level is 0.95. And then hit calculate, and it'll give you the same confidence interval. And in fact, if you go up to 5 decimals, it gives you 0.81003 and 0.87397. So again, we always round to 3 decimal places, so we get the same thing. So this would be a 4. So we get the exact same answer. Okay? So I hope that helped. So now let's do another one. So let's do this one. So let's see, it says, suppose 250 randomly selected people are surveyed to determine if they own a tablet. Okay. It says, suppose, oh, I'm not going to write this out. You can pause it and listen. Okay, it says, suppose 250 randomly selected people are surveyed to determine if they own a tablet. Okay, so now, what's the sample size in this case? Well, the sample size is 250, right? So n is 250. And we're interested in the proportion of people who own tablets. Okay, so now of the 250 people surveyed, 98 reported using a tablet. That's going to be our x value. So x is 98, which means our n minus x is equal to what? Well, it's going to be 252, right? And remember, this is the same as n minus p hat. This is the same as n, excuse me, not minus, n times p hat and n times q hat. Okay, so again, all 3 of our checks are satisfied, right? N is bigger than or equal to 30. N times p hat is bigger than or equal to 15, and n times q hat is bigger than or equal to 15. So we know the sampling distribution of p hat then is approximately normal with a mean of p and a standard deviation of pq divided by n. So that's what we know. So again, all all three of these give it to us. Okay, and again, this is, again, the central limit theorem applied to proportions. Okay, chapter 7. So now, what do they want? They want, again, a 95% confidence interval for the true proportion of people who own tablets. Okay, so that's what P represents. So how do we do this? Well, let's use the calculator. Okay, so let's use the calculator. So the calculator is, we're going to use 1 prop z int, because we're talking about a confidence interval for P. So this is the function on our calculator we'll use. Okay, and remember, this is located under stat tests, and then just scroll down until you find it. And then in this case, remember, the three things we're going to put in is we need to put in x. What's x in this case? 98. And then n is 250. Oh, hold on a second. I mean, it can't be 252, it has to be 152. Okay. Oops. Okay. So, yeah, so 152 plus the 98 gives us the 250. Okay, so n is 250, x is 98, and then of course our confidence level, which is 0.95. Okay, and again, if you're using the formula, just remember, a 95% confidence interval always gives us a critical value as z alpha divided by 2 of 1.96. So remember, some of these you can just remember. Remember that there are the ones that we're going to keep using over and over again, the common ones. Okay, for confidence intervals, it's going to be 90, 95, 98, and 99, and also sometimes 80. So always, we're going to get used to seeing those. Okay, so some of these you're going to know just by the fact that we've been using them over and over again. So 95% confidence level always gives you a critical value of 1.96 for confidence intervals. Okay, if you're talking about a 90% confidence interval, then you're going to have a critical value of 1.645. If it's a 98% confidence interval, then you're talking about 2.33. If it's a 99% confidence interval, then you're talking about 2.576. And if it's an 80% confidence interval, which is not used that often, but it's going to be 1.28. Okay, so again, you can use the table or the formula, the calculator to get it for you, or some of these you're just going to know, and that's fine. If you know it, you know it. If you're ever in doubt, just go to the table or use the calculator. Okay. But in this case, we are going to use the 1 prop z in, because then all we have to do is just plug in these values and it gives it to us. Okay? So in this case here, what do we get? Well, if we plug that in, we're going to get, well actually I don't know what we're going to get because I don't have my calculator. So let's do this by hand. I left my calculator on the car. So again, okay, so let's do it by hand. So that'll be good practice. So now we're going to use P. So I'm going to leave you guys to use the calculator. I'm going to use the formula, and then you compare with the answer. Should be the same. So I'm going to use P hat plus or minus z alpha divided by 2 times. Now I'm going to use P hat times Q hat divided by n. Okay, so first thing I need is P hat. Okay, well what's P hat? X divided by n, and so this is going to be 98 divided by 250, which this is going to be equal to 0.392, if I'm not mistaken. So if you multiply this by 4, you get 1,000. So if you multiply this by 4, you get 360 plus 32. Yeah, so it's 0.392. And then Q hat is just going to be 1 minus that. So Q hat is going to equal 1 minus 0.392, which is going to be 0.608. Okay. So now I've got all my information. So I'm going to just plug and chug. So this is going to be 0.392 plus or minus 1.96 times 0.392 times 0.608 divided by 250. Okay. Now, again, this z alpha divided by 2, if you don't remember, use the table or use your function inverse norm. Okay. So practice, 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 practice. Okay. Okay, so now what do? I'm just going to multiply this out. And let me figure this out real quick. Of course, I don't turn on the computer. And I pick a problem that's not doesn't have a solution, which is fine. But these are the right numbers. So this is the setup. So I don't have my calculator with me. So c'est la vie. So here's the setup. So all you guys have to do is plug and chug, and you should get the same answer as if you used one prop z int. Okay. So I'll leave this for you to finish. And I'll probably just stick with some of the ones that have the solution. But this is a good one. I like this one. But again, I'm going to actually probably do more of these with the formula and then use the calculator, because you guys can just use the practice calculator getting the same answer. Okay? So let's see here. So let me get into here real quick. Okay, so let's stop that. So the answer is this pretty much, and just simplify that, and then understand how to interpret the confidence interval. Okay, so again, if you have any questions, reach out to me, but I've got it all set up. All you have to do is just plug it in your calculator. This is the margin of error piece, and then you're just going to add and subtract from the point estimate, which is 0.392, and you're done. So just keep that in mind, and you should be fine. Well, is this loading up real quick? I think this is loading up real quick. Okay, so that's going to work for this one. And hey, by the way, you never know if something like this may show up on an exam. Okay. Okay, so the next, let's see what we've got here. What do we got going on? Let's do let me see here. Let's do this one. So in this example here, it says, for a class project, a political science student at a large university wants to estimate the percentage of students who are registered voters. He surveys 500 students and finds that 59.7% are registered voters, computing 90% confidence interval for the true percentage of students who are registered voters, and interpret the confidence interval. Okay? So now, let's write down the information in the problem. Always, always write down the information in the problem. Okay? That's always the thing that I would do. Okay? So let's do that. So what is the sample size? 500. So n is 500. Okay? So now, of the 500, he finds that 59.7% of them are registered voters. That's your p hat. So always read the problem carefully and make sure that what they're giving you. Okay, so in this case, he found that 59% of what? The 500 students are registered voters. So that percentage is p hat. So p hat is equal to 0.597. Always want to write it as a decimal. Write it as a decimal. Now, he wants to compute a 90% confidence interval for P. What's P? P is the true proportion of students at this large university who are registered voters. That's P. Okay? Now, we want to know the distribution of P hat, right? That's the whole purpose. We can't construct a confidence interval for P unless we know the distribution of P hat, and specifically that it's normal. So here's where our conditions come in, right? So 1, n is bigger than or equal to 30. Yep, check. 2, n times p hat is bigger than or equal to 15. Well, that's x, right? Well, how do we find x? Well, x is what? X, well, that doesn't apply. So here, x is equal to n times p hat, which is going to be 500 times what? 0.597. Okay, so that's going to be equal to approximately, well, let's do this. If we multiply that out, that's going to be equal to 298.5. Okay, now that is 59.7% or 0.597 of this. 250. Yeah, so it's going to be 298.5 students. Okay, so now I'm going to come back to that in a moment. So now, oh, actually, no, might as well just say it now. So here, when it comes to your calculator, we cannot put decimals into your calculator because when you use one bar stats, not one bar stats, I'm sorry, when you use one prop z int and you have to put in x and n, well, you can't put in decimals. It has to only be whole numbers. If you try to put in a decimal, it'll give you an error. Okay, so we have to put in whole numbers. So we might as well round this up to 299. Okay? And then obviously this is bigger than 15, so check. And then the third one is n times q hat, which is equal to n minus x, has to be equal to greater than or equal to 15 as well. Well, if we subtract this from 500, right? So n minus x is going to be what? It's going to be 201, which is definitely bigger than 15. So we've got our checks. And so what does that tell us? It tells us that p hat is normally distributed with a mean of p and a standard deviation of the square root of pq divided by n. Okay, so it gives us that. Okay, so just keep that in mind. Okay, so we've got this, okay? And so now we can use this to construct our confidence interval. So we want a 95% confidence interval for P, so it's going to be P plus or minus Z alpha divided by 2 times the square root. And now this is where the standard error goes in. So it's going to be P hat times Q hat divided by N. So it's the square root of this. And that's our standard error. Okay. And so now we're ready to use the formula or to use one prop z int. So again, one prop z int, all we have to put in is x, which is equal to what? 299. And then n, which is equal to 500. And then our confidence level, which in this case is 0.90. And then you just hit calculate and you're done. Okay? And what you're going to get, is, to use the calculator, you're going to get 0.562, if you round to 3 decimal places, comma 634. 0.634. Okay. And so if we change this to percentages, and I always recommend changing them to percentages, this will be 56.2% and 63.4%. And then the interpretation is again the same. We can be 90% confident that the true proportion of students who vote, right? That's what we're talking about. The true proportion of students at this large university who vote is somewhere between 56.2% and 63.4%. Okay? Now, that's using the calculator using one prop z int. Now again, if you use the formula, you'll get the exact same answer. So if we use the formula, which is this, then all we have to know is what is p hat. Okay? In this case, we know p hat. It's 0.597. And so we know q hat, which is, what is q hat? Well, q hat is then going to be equal to 0.403. Okay, 1 minus p hat. And so we've got those two, we've got n, all we need is z alpha divided by 2. So again, if you use the z table, or if you use inverse norm, you're going to get the same value, which in this case is going to be 1.645. Okay, that's going to be your z alpha divided by 2. Okay, so remember how to use the calculator. So again, let me just draw the diagram for you guys. Okay? So again, the confidence level tells you the middle area between your critical values, right? So this is z alpha divided by 2. This is negative z alpha divided by 2, right? It's symmetric and bell-shaped, right? So we know that 90% or 0.9 of the area, 9/10 of the area is between these two critical values, which means what's alpha? Alpha, remember, is the area in the tail, right? Or in the tails, I should say. So alpha here is 1 minus 0.9, right? So alpha is 1 minus 0.9 or 0.10, and then half, because remember, bell-shaped and symmetric, half goes into each tail, so that means 0.05 is here, 0.05 is here, and so what's the area to the left of this critical value? 0.9 plus 0.05 equals 0.95. This is what you want to put into the calculator, okay? Or look up on the z table. Okay, so you want to find the number closest to 0.9500 on the table, or plug in 0.95 into your inverse norm function for the area to the left. And then remember that the other two arguments is the mean and standard deviation, which is 0,1 for the standard normal distribution. Okay, so that'll be the last time I go through this. Practice these guys, practice. Okay? Okay. The idea is if you practice all these, you'll have multiple tools in your toolbox that you can solve these problems any which way you want, whatever way makes sense, and you'll always get the correct answer regardless of which way you decide to do it. Okay? Okay, so now what do we do? Let's plug and chug. So it's going to be 0.597 plus or minus 1.645 times the square root of what? It's going to be 0.597 times 0.403 over 500. And so if we calculate this, we get 0.597 plus or minus, and the margin of error turns out to be 0.036. So it's 0.036. And then, of course, our confidence interval then becomes hold on a second. .561 and 0.633. And that's our confidence interval. And of course, we're going to write it as a percentage, so it's 56.1% and 63.3%, which is what we got before. Okay? So that's the answer. Okay. So now, again, the interpretation is the same, right? So in this case here, we're 90% confident. We're 90% confident that the true proportion of students who vote, who are registered voters at this large university, is somewhere between 56.1% and 63.3%. Okay. And that's it for that problem. So now, let's see here. So one note I think that is important for proportions, and it has to do with the accuracy of a proportion, because there is a certain amount of error that is introduced when constructing confidence intervals for a proportion, okay? And because we don't know what the true proportion is, and so we have to use the sample proportion in our calculation for not only the point estimate for the center, the mean, but we also have to use it as part of the standard error or the standard deviation, but we're now using the standard error. So there's a little bit more error involved for confidence intervals. Okay, so we have to take that into consideration. Okay, so because we don't know the true proportion of the population, then we're forced to use the point estimates to calculate the appropriate standard deviation of the sampling distribution. And so studies have shown that the resulting estimation of the standard deviation can be flawed. Okay, so now there is a simple adjustment that allows us to produce more accurate results for our confidence interval. Okay, and what we're going to do is we're going to simply pretend that we have 4 additional observations. Okay, this is the rule of +4. Okay, so basically we're going to add 4 more observations to each of the sample size. Now the way it works is we're going to add 4 to n. So we're going to add 4 to the sample size, but what we're going to do is add 2 to the number of successes and 2 to the number of failures. Okay, and this is sort of like a continuity correction, like we talked about with the binomial distribution when we were talking about the normal approximation. You can look at it the same way. It makes our confidence intervals more accurate. Okay, so in real life, we actually use those corrections for confidence intervals when we're dealing with these sorts of things. Okay. Now with large data sets, it won't matter, but for these types of data sets, it's a good practice to do. Okay. Let's see here. So let's use a quick example, and I'll just show you how this works. Okay. So it says a random sample of 25 statistics students was asked, have you smoked a cigarette in the past week? 6 students reported smoking within the past week. Use the +4 method to find a 95% confidence interval for the true proportion of statistics students who smoke. So again, look at what we have. We have a sample size of 25 students. Not a big sample size. Okay? Let's see here. Okay, one other thing too is the rule of 4. It says computer studies have demonstrated the effectiveness of this method, and it should be used when confidence level desired is at least 90% of the sample size is at least 10. Okay. So again, it should be used when the confidence level desired is at least 90% and the sample size is at least 10. Okay? So that's the protocol. Okay? So in this case here, we have a sample size of 25 students. Okay? And 6 of the 5 students reported smoking in the last week. So we're going to use the +4 method to find a 95% confidence interval for the true proportion of statistics students who smoke. Okay, so now 10 out of the 25, 6 out of the 25 Yeah, there's typos in here. Hold on a second. Let me just make sure what numbers they're using. Yeah, they're using 10. I think it's a typo. So 10 students. Okay, so we're going to use 10 because all the solution uses 10. And I just want to be consistent here. So it says, so we're going to say 10 out of the 25 students said that they smoked a cigarette in the last week, in the past week. So again, correct that. So the number of students who reported smoking a cigarette in the past week is 10, not 6. And the sample size is 25. And so that's what we're going to use. Okay, and we're going to calculate a 95% confidence interval, and we're going to use the rule of 4 in this case. Okay, so we want a 95% confidence interval for P. And in this case, P represents the true proportion of students who smoke. Okay, so we know N is equal to 25, right? And we know X is equal to 10. So what we're going to do is we're going to add 4 to N, right? We're going to use the rule of 4. We're going to add 4 to N, so this will make this 29. Oops. And we're going to add 2 successes to the 10, so 2 more people that smoke, and that'll make this 12, which means that N minus X, right, the new N, is going to be what? Well, it's going to be 17. Okay, so that's the new information. So if we use one prop z int, so one proportion z int, with the new information, we're going to use this, and we're going to use this, and this. So basically 29 and 12, right? Because in this we need X, N, and the confidence level. So X is going to be 12, not 10. And N is going to equal 29, not 25. And then we're going to use 0.95. And what do we get for our confidence interval? We get 0.235, comma, 0.593, or 23.5% to 59.3%. So large swing. So large swing in the proportions, right? So again, we are 95% confident that the true proportion of students who smoke is going to be somewhere between 23.5% and 59.3% of the students. And that's it. So again, that's just an example of how we would use the rule of 4. So again, this is typically used for sample sizes that are, hold on a second. For confidence intervals that are 90% or higher, and for sample sizes that are at least 10. And that's it. Okay, so I just wanted to show you that. And let's see here. Now, the next thing is sample size. And this will be the last thing we talk about, because with the mean, we had a formula for minimum sample size. Well, now that we're dealing with proportion, we're going to have a different formula for minimum sample size because it's based on proportions, not averages. Okay? So, the minimum sample size, so we're going to, again, it's all based on the margin of error. So the margin of error calculation is z alpha divided by 2 times the standard error, which is p hat times q hat over n. Okay, so since this is our margin of error formula, our minimum sample size formula will be formulated or derived from this formula. So we're just going to solve for n. So the minimum sample size is n is equal to, and in this case, we're going to end up with z alpha divided by 2 divided by the margin of error, quantity squared, times p hat times q hat. And that is going to be our minimum sample size formula when we are dealing with proportions. Okay? So let's do an example. It says, oh, by the way, remember the key word for the margin of error is within. So if we say we want to make sure that we're within 3% of the value of p hat, or we don't want to be any further than 0.3% away from the true value of the proportion, then that's going to be margin of error. Or we say we don't want to be any further away than 3%. Okay, so those are key words for margin of error. If the proportion, if the p hat is not stated in the problem, this is one of the times where if we're not given the preliminary information of p hat, then we always assume that p hat is 0.5. Why do we do that? Because if we don't know, then we're going to make this value as big as it possibly can be. Based on a fixed, so this is going to be fixed, right? So we're going to be given this, and this will be fixed too because we're going to be given a confidence level, right? So since we're given a confidence level, this will be fixed, the margin of error will be fixed. So the only thing that can affect the minimum sample size is P and Q, right? Or specifically P, right? Because P determines Q. So if we don't know P, well, then we want to make sure that we bound N to be as big as possible. And the value that will make this product here as big as possible this value here is if we make them the same at 0.5. Okay? And you can play with your calculator. Take any combination of the two proportions that add up to 1, right? So 0.5 times 0.5, 0.4 times 0.6, 0.75 times 0.25, 0.9 times 0.1. Take any combination of proportions that add up to 1, multiply those together, and you'll always get something less than 0.25. Okay? So if we don't know p hat, or the problem doesn't tell us p hat, we're always going to assume that p hat is 0.5. Otherwise, use what they give you. Okay, so enough of that. Here is the example. Suppose a mobile phone company wants to determine the current percentage of customers aged 50 plus who use text messaging on their cell phones. How many customers aged 50 plus should the company survey in order to be 90% confident that the estimated sample proportion is within 3 percentage points of the true population proportion of customers aged 50 plus who use text messaging on their cell phones. Okay, so let's break this down. So, what's the confidence level here? The confidence level is they want to be 90% confident. So the confidence level is going to be 0.9. And they want to be within 3 percentage points, which is the same as 3%, right? So they want to be within 3% of, or they don't want your p hat. So here's it. They don't want your sample statistic p hat to be more than 3 percentage points away from the true value. That's the maximum distance, okay? So they don't want our p hat to be any further away from the value than either 3 percentage points this way or 3 percentage points that way. Okay? So this is the margin of error. Okay? So now, let's see here. They don't tell us p hat. So in this case, we're going to use 0.5 because they don't tell us what p hat is. They don't give us any information about p hat. So we're going to use 0.5 as p hat. So that means p hat is going to equal q hat, which is going to equal 0.5. So now, what do they want? They want to know what's the minimum number of people that they need to survey in order to make sure that the margin of error is no bigger than 3%. Okay? Well, this is the formula we're going to use, right? Well, in this case here, we know the margin of error, right? That's 0.03, right? 3%. We know the P and Q hat, those are going to be each 0.5 because they don't tell us any information, so we're going to make them 0.5. The only thing we don't know is Z alpha divided by 2. So remember, use the table or use your calculator to get Z alpha divided by 2. This is one of the cases where you're not going to have a formula or a function on your calculator that's going to spit it out. Okay, that's going to spit out the margin, the minimum sample size. Okay, so in this case, we can't get around of figuring out what Z alpha divided by 2. But if you recall, we know that for a 90% confidence interval and a confidence level of 0.9, that the confidence or the critical value is going to be for Z alpha divided by 2 is going to be 1.645. Again, use inverse norm. Make sure you put in the correct area, okay? Or if you use the table, make sure you look up the correct area to the left, and you'll get the same answer. Okay? Now, if we, got to square that. Okay, so now if we do this, what are we going to get? Well, we're going to get equal to 751.7. Now remember, just like before when we talked about minimum sample size involving the mean, same rule applies here. Always round up. So the minimum sample size in this case is going to be 752 people. And that's what we need to have. Okay? So if we make sure that we survey at least 752 people, then that will guarantee that we will be no bigger than 3% away from the true value of the parameter P with a 90% confidence. Okay. And let's see here. I think that's it. So that wraps up Chapter 8 on confidence intervals. Please review these as many times as you need to. Do the examples. Do them without looking at the solutions first, and then see if you can get the correct answer without looking at the solutions, and then go from there. That will be the best feedback to see whether you know these or not. Okay? If you have any questions, reach out to me, or just review the video and go from there. We'll see you next time. This wraps up Chapter 8. Next time, we'll start Chapter 9, which is all about hypothesis testing. See you then. Bye.